I tried to show you in an earlier class, but the way I was doing this project then was by downgrading OpenSSL to an old version, and the libraries I needed were not easy to find anymore. So I went to the project and I figured out how to do it with the modern version of OpenSSL. So that's much better. So I'm glad, I'm glad to do this now. I finally have quit using old versions of stuff, which I hate to do. So we're going to generate an RSA key. We talked about this before. You have P and Q, you multiply them together, that's N. And then you just pick E for a public exponent. Usually you just use 5, or any prime number will typically do. And the private key is calculated by D times E is 1 mod phi, and phi is this number, P minus 1 times Q minus 1. So that's a summary of RSA keys. But really here, the point is just to notice the things that make up the key is P and Q, and E, N and E are the public key, and P, Q, and D are the private things you need. If you know P, you can figure out Q, and if you know P and Q, you can figure out D, and D is the decryption key. So now the point is, like I've said before, I always have seen these things here, these private keys that look like this. And I always wondered, what is this garbage? And this turns out to be something called the ASN1 format. And it is standard format for encrypting data, and for an RSA key, it looks like this. And this is right from the RFC that defines this. So it is a ASN type 1 blob of base 64, and it encodes this stuff, N, E, D, P, Q, and some other numbers. So that's what it is. And here's, it is just these numbers. Like I say, P and Q are the prime numbers that you multiply to make N, E is the public exponent, and D is the decryption key. So these numbers here are the fundamental numbers you need for RSA, and these things down here don't really matter. They can easily be calculated from the ones above them. They're just numbers that are convenient to use in the mathematics. But that's what's going on. So we can extract those from these things. So we can play with it, and now we can do it all with OpenSSL. So this will create a 512-bit RSA key, which I was talking about. This is let me make a new notebook here. I figure out how. There, File, New Notebook. All right, I close the old one. All right, so here this will make a new 512-bit RSA key, which, as I mentioned, is the original link they recommended. This is no longer considered secure, but it's enough so we can see how it looks. Okay, there it is, a 512-bit key. Notice something. My example is here. And if you look at, say, the end, I have ZUA, and here it's all different. But if you look at the beginning, it's exactly the same, MIIB. And that's because the beginning is just like a label. That is always the same. Remember, the thing about base 64 is it only encodes a few letters at a time. Every 4 letters of base 64 give you 3 ASCII characters. So the first 3 letters are the same. Is what this is telling you. Anyway, so this is the blob form, which is, of course, easy to save in a file and email and all that. But to understand what's inside there, you have to convert it into a PEM file, privacy enhanced mail. That's what we're going to do. So this will generate a new one, but it's going to generate it in PEM format. And then we're going to look at that key with cat, and then this one here is going to take it apart to let us see what's inside there. This is what I didn't know how to do. It's OpenSSL RSA. That's what opens these ASN1 formatted files and lets you see the internal contents. So this is going to generate it, saving it in a file called key.pem. It's going to show us that file, and this is going to open that file and show us the numbers that are hidden inside it. So there we go. Whoops, didn't get my copy correct. Over here, copy. Over here, paste. Nope. The browser often does this. The key press doesn't work. You have to use the mouse. I don't know why. That's a common flaw. Anyway, all right. So there's my key, and I made a new key. So it doesn't end with ZN, but it always starts with MIIB. And here's opening it up. With this OpenSSL RSA command, here it shows you. So the modulus is E. Oh, no, this is N. N is modulus. Here's E. Here's the public exponent. That's E. So this is the public key. This is N, and that's E. And here is the private exponent, which I think is D. I labeled them here. Yep, that's D. This is D, and here's P and Q. And there's some other numbers down there. So that's the point. Anyway, you can see inside there, and they're all expressed here as hex values with colons to separate the bytes, whatever format these guys decided to use. That's the game. All right. So now that's the private key that we've created. We can now look at the public key. And this, by the way, includes, of course, both the private key and the public key. The public key is just N and E. And of course, you wouldn't want to send this to anybody because that's got P and Q in it. You have to send the public key to people so they can use it. So you generate the public key from the private key, and you do that this way, pub out. Just tell it, I'm using RSA, read this private key, and output the public key. So that's here. And you see the public key is, of course, much shorter. All this has is N and E. This has N and E and P and Q and D and all that other stuff. All right, so this is what you would send people. Here's my public key. Now you can send me messages, and nobody else can read them. All right, and so now you can put the public key in a PEM file, print it out and parse it. You can also open the public key the same way. This will create another public key from it, same as you did before, and then look at that key and then extract the contents with RSA. So there's the public key file, and here's what's inside it. It is the modulus and the exponent, and that's it. N and E, as you expect, in a blob form. So that's the game. And of course, those keys are not secure anymore. This is what we need to be using. We need to be using at least 2048 these days. So this is what a 2048 key looks like. Just much longer. Yeah, just much longer, of course. And here you see the public key, which will also be much longer. That's the public key. This is the inside, that's the modulus and the exponent, and there's the base 64 form. So that's what's going on. And now what people often do is you encrypt the private key. You don't want to just save it on your machine. You want to password protect it. So every time you use it, you have to type in a password. And then if somebody gets on your machine or they infect it with malware and steal it, they still won't be able to get in. That's the idea. So this is how you encrypt it. This will generate a 2048-bit encrypted private key file, and it will protect it. I think this is where you protect it with AES 256. So it's going to add AES encryption on the key, and it's going to ask you for a password. So that will do it, and then print the answer. So if I run this, there, it's going to generate it. Now it's going to ask me for a passphrase, so I have to type in my password, enter, and then it's going to make me do it again, which is a good idea, because if you get it wrong, you'll be locked out. And there we are. That's now the encrypted private key, and notice it tells you that, begin encrypted private key. So this is not just a private key, it's encrypted. You need to take a password, and then it will decrypt into the usable stuff. So that's the game, and whenever you use it, you'll have to supply the password. Now I saved that as a file called key3. Here I'm going to open the key3 file to generate the public key, so I'm going to have to provide the password. You can never use that file without providing the password. That's the whole point. So to ask me for the password, whoa, and somehow my GUI went somewhere crazy. There we are. Okay, there. And now that I gave it the password, it's able to make the public key. And the public key is, of course, shorter than the private key. So that's the game. And now you've got some challenges. Here's one where you can just find P from the private key. It's just in there. All you have to do is open it. Here you have to find the public key from the private key, which is pretty simple. And then you have a tougher one where I've redacted part of this. And you're going to have to find Q. And what you'll find is for one of these, I think this one here, you'll be able to figure out Q pretty easily. There's one down here that's going to be much harder, where I've actually removed part of it, and you're going to have to do a brute force search some of the bits are missing. You have some of the bits, but not all the bits, so it's possible, but you will have to fill in some missing bits. And there are various ways to do it. I can tell you my sleazy technique. The way I did it was to find out what was going on. I just replaced all these X's with capital A's and ran it through taking it apart, and then I replaced it all with Z and see what changed. That's how I did it. You could be more scientific about it, but that's how I figured out what was missing, was by just replacing these with two values and comparing them to see what changed. And then I could see, you know, I have N and I have the first half of P, but I don't have Q, something like that. I could figure out what I've got. And that's how I did it, but a more clever way would be to actually carefully count your way in and figure out exactly what bits you're missing. You could do that, but I did it the cheap brute force way. That's how I usually do things. I don't like to think too much. I just use a simple technique that gets you to the end. Yeah, but you know, you could figure out exactly what these bits are, but I didn't. Anyway, there are various ways to do it. All right, now I say you can get some extra credit by doing the more difficult one, where you're actually going to have to do a brute force through maybe a few million guesses. It's not too hard. Python can do it, but you don't have to do anything impossible like 128 bits. That would be impossible. You're missing something like 32 bits, so it won't take forever. Anyway, that's what I wanted to show you.